Imagine sprinting down a narrow hallway where turning around is physically impossible. You can only move forward, one step at a time. A singly linked list is a sequence of data nodes connected by strict one-way pointers flowing to a dead end called null. If a search algorithm steps past its target, it cannot step backward. It must snap back to the beginning and restart. Real-world applications require more flexibility. Features like an undo button in a text editor or dynamic memory management rely on structures that can move both forward and backward at will. A basic one-way list is simple to build, but it lacks the maneuverability required for the complex, unpredictable tasks of modern software. To solve this one-way problem, computer scientists introduced a structural upgrade, the doubly linked list. This diagram breaks down the anatomy of a single node. Instead of holding data and one arrow, it is divided into three distinct fields. The center holds the value, the right points next, and the left pointer stores the previous node's exact memory address. When you string multiple nodes together with these dual pointers, you create a two-way highway. Algorithms can slide up and down the chain, reversing direction instantly. This single backward reference allows an algorithm to pivot mid-search. In applications that update frequently, the system avoids the processing overhead caused by restarting a traversal every time the target shifts. Even with a two-way street, straight-line lists still reach a hard limit. Eventually, the pointers run out of data and hit a null pointer. To keep operations moving without interruption, developers implemented another architecture, the circular linked list. Instead of pointing into a void, the final pointer arcs back to lock into the first node. With no terminal end, inserting data is localized. You isolate the spot, drop in a new node, and update the surrounding pointers to incorporate it. By seamlessly looping the tail back to the head, programmers turn a finite sequence into a perpetual circuit. At the macro level, these underlying structural choices support the way modern operating systems juggle multiple background tasks. That continuous loop architecture powers circular queues, allowing your system to cycle through resources without needing to manually reset once it reaches the end of the line. Meanwhile, the bidirectional freedom of a doubly linked list serves as the foundation for complex algorithms like Fibonacci heaps, which are used to prioritize tasks in large-scale network routing. These structures allow for precision edits, letting an algorithm slice out one specific node and reconnect the surrounding links without needing to rebuild the entire dataset. The logic of internal pointers provides a specialized solution for data movement. Rethinking the direction of a single link is a quiet but effective way to maintain the high-frequency updates that modern computing demands.